You've learned how to recognize a carbohydrate in its open form, that it's either an aldehyde or a ketone, and drawn in the Fischer projection that goes at the top, and then the rest of the carbons hang down, and there's an alcohol on each carbon that doesn't have the carbonyl. And then we know that how to identify a D sugar by looking at the second carbon from the bottom and noticing that the hydroxyl is on the right. But this open form of sugars is not really the way that they're typically drawn. They're typically drawn in rings. The open form is not the most stable form. The most stable form is the ring form, and that is the form which enzymes will take and use the carbohydrates, and so it's considered the standard form for them. Now, the carbohydrates will form either 5-membered or 6-membered rings, and they will make all of them. Only certain rings are what the enzymes will use, though. So you're going to see each of these sugars written in a particular ring form. Glucose forms a 6-membered ring, and it's written over here. This is called a Hayworth projection, and this is one of the forms of glucose in its ring form. Let's look and see how this occurs. Notice this oxygen right here, the oxygen that determines whether it's D or L, becomes part of the ring. And what you can visualize is that this oxygen is, of course, this chain of carbons is bending backwards, and this oxygen right here goes back behind all this and attacks that carbon that in the carbonyl. And this oxygen was that oxygen that was in the carbonyl. And this group right here now is what's called a hemiacetal. The oxygen from this here and the oxygen from that there. And this carbon is right here. Okay, so what we're going to do is we're going to look and see how we can take these open chains and form them into rings. Okay, so here is glucose written with all of the oxygens in different colors, so it's easy to identify what happens. What we're going to do is we're going to take this Fischer projection, we're going to turn it on its side. It's no longer a Fischer projection when we turn it on its side, but we retain the up and down that the right and left are in the Fischer projection. So if I go and I take this and bring this carbon down and that carbon up, you can see that would put the yellow hydroxyl down, the green one up, and the blue one down. And then this oxygen, the chiral, the DL oxygen, that's in the ring. All of the D sugars have this hydroxyl on the right, and when it forms a ring, which is, it's always going to be the D alcohol that forms the ring, that puts this methyl hydroxy up. So you can recognize a D sugar by seeing this methyl hydroxy up in the air in the Hayworth projection. When the ring forms, attack can come either from the top of the carbonyl or from the bottom of the carbonyl. If it comes from the top of the carbonyl, the hydroxyl will be down, and if it comes from the bottom of the carbonyl, the hydroxyl is up. And these two forms are called anomers. This is called the alpha anomer, and this is called the beta anomer. Alpha is down, beta is up, and I remember BUP, as in puppy, for beta up. You can do it whatever way you want. Okay, so we get these two forms from D-glucose. This one's called alpha D-glucose, that one's called beta D-glucose. So you have two different rings that can form, and they interconvert in water. Solid glucose, when dissolved in water, if it's all alpha, when you dissolve it in water, what happens is the ring ring will open to the chain form and then reclose, and you'll start making beta. And there is an equilibrium concentration of alpha and beta that gets established with time. Same thing happens if you have all beta glucose and you were to dissolve it in water. Eventually you're going to get a mix, same proportion of alpha and beta glucose over time. So the interconversion between alpha and beta glucose is called mutarotation. So whenever you put solid glucose in water, you have mutarotation ongoing and you get an equilibrium concentration of the alpha and beta ring forms, regardless of what you start with. Okay, so we've seen that we can get both alpha and beta anomers from in a Haworth projection. If you have an aldehyde, this used to be an aldehyde, see it's the number 1 carbon with 2 oxygens on it. This was an aldehyde, it forms the hemiacetal. And this was an aldehyde, it's forming the beta hemiacetal. You can have this happen with the ketones also, and then there are hemiketals that form. The Haworth projection is very easy to draw, but the chair form is really the way that the glucose molecule exists. And you can see drawn here, we can have the alpha form in the chair conformation or the beta form. When you look at glucose in the chair form, you can see it's still going to be, when you move from the number 1 carbon to the number 2, 2 is down, 3 is up, 2 is down, and then we have the chiral, the D carbon, the carbon that makes this the D sugar. So the hydroxymethyl group is up back there. So this is down, up, down, down, up, down. This is alpha, that's beta. It's just the same thing as the Haworth projection, except you're actually seeing how it really exists. If we look at fructose, it can form the ring also, but notice if we take this, the alcohol group that identifies it as being a D sugar, and we form the ring, we're going to have this oxygen connected to this carbon, to this carbon, to this carbon, and this carbon, and you can see that's a 5-membered ring. 1, 2, 3, 4, 5. So we're forming only a 5-membered ring. Here is this oxygen that was on the D carbon, and it forms a bond to this what used to be the ketone. Notice you can tell this was a ketone because this carbon that has the 2 oxygens on it has 2 carbons attached. This is fructose. We know that it's fructose because this is going to be left, right becomes up, down. And so it's very easy to remember how to draw fructose. Now, the hydroxyl group is up here, so this is beta. We do not look at the methyl hydroxyl group that forms. We look at the hydroxyl group. So this is beta D-fructose. This is going to be alpha D-fructose. And it just takes a little practice in order to learn how to take an open chain one to the closed chain one. I have another screencast-o-matic online video available that goes through this in a little bit more detail as I draw it for you, so you might want to watch that. Here's galactose. Notice it's right, left, left, right. This is the oxygen that forms the ring. So when we turn this on the side, this is going to be the right, left, left becomes the down, up, up. Here we go. Here is the carbon that used to be in the carbonyl, then down, up, up. Easy way to do it. Of course, this is alpha, and that's beta. This is the anomeric carbon in the Haworth projection. If we go back to fructose, the anomeric carbon is always drawn on the far right of a Haworth projection. Here is ribose. Notice ribose is right, right, and then, of course, you have the D-hydroxyl. So here is the carbon that was in the carbonyl. The right, right becomes down, 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 down. So here's ribose. This is beta ribose, alpha ribose. And of course, it's a 5-membered ring. 1, 2, 3, 4, 5 is what must form. Okay, so this is a picture of mutarotation occurring. Here we have the alpha glucose, and here we have the beta glucose. How do they interconvert? When you put them in water, they open ring and then reclose. And they can flip from alpha to beta, or beta to alpha, or go alpha back to alpha, or beta back to beta, and you get an equilibrium concentration of the alpha and beta anomers.